Welcome back. The objective of this video is to fine-tune our techniques for analyzing graphs of rational functions. We'll expand on finding zeros, and we'll take a little peek at graphing them. Again, in review, characteristics of rational functions. If they have no common factors, then the rational function is said to be in lowest terms, and we know these characteristics apply. R of x has zeros when the numerator of x equals 0. And R of x is undefined when our denominator of our function is equal to 0. So these will be our vertical asymptotes when the denominator equals 0. And those will be our restrictions on the domain. And our zeros are when the numerator equals 0. And those will be our zeros or our x-intercepts. Example 1 says, use the procedure above to find the zeros of the rational function. State the end behavior using limit notation. We'll probably do a little bit more than that. But let's go ahead and factor our numerator and denominator. And our numerator factors to x plus 4 times x minus 3. And our denominator factors, it's a difference of 2 squares, so that just factors to x plus 1 times x minus 1. So the zeros, or x-intercepts, those are going to be the numerator. We set that numerator equal to 0 after we factor it, and our zeros are equal to x equals negative 4 and x equals 3. And we might plot those on our graph at negative 4 and 3. And then finally, our restrictions on the domain, they don't ask for that, but I'm going to do that here. Our denominator can't be equal 0. Denominator can't equal 0. So we factored that guy, and we get x can't equal plus or minus 1. And those will be our vertical asymptotes. So we actually have vertical asymptotes on our graph at x equals plus or minus 1. So you might see a vertical asymptote, something like that, at x equals plus or minus 1. And then finally, we're asked for the end behavior. So essentially, they're asking us to find the horizontal asymptote. So our end behavior, we have to consider just x squared. That's 1x squared over 1x squared. Our battle between the numerator and the denominator. Well, as x gets really, really big, these are going to battle to a tie. This simplifies to 1. So using limit notation, the limit as x approaches negative infinity of x squared over x squared equals 1. And our limit as x approaches positive infinity of x squared over x squared, that also equals 1. So we have a horizontal asymptote at x equals, or pardon me, at y equals 1. And a little bit of coincidence that these are all 1s, but that's easy to factor and numbers that are simple to work with. Sample 2 asks us to construct a function from its graph. So we're going to work backwards here. Now that we have the graph, we want to work backwards to the function. So a couple things we can note right away. We have a 0 at x equals negative 3. So that would create a factor of x minus a minus 3, or if you will, a factor of x plus 3, and that's going to be in our numerator. We have a vertical asymptote at x equals 3. Okay, which means that's a restriction on our domain. So that means the denominator is going to have a factor of x minus 3. So right now, we've got x plus 3 over x minus 3. We have a horizontal asymptote of y equals 1, which means the highest degree in the numerator has to equal the highest degree in the denominator. Okay, so we got to have something like x squared over x squared, or x cubed over x cubed. And since it's 1, the coefficients on these have to be the same. Well, we're sitting pretty here with x plus 3 over x minus 3. And then we also have a y-intercept at -1, at 0, -1. And that, when we put 0 in for x, do we get -1? We do. So it is possible that our function is simply x plus 3 over x minus 3. So we did a nice job building that one. We'll get some more practice with this when I see you in class.